the last thing that we are going to look at in the context of functions is this notion of what is called recursion. Okay. So, in order to understand recursion, first we need to understand what exactly is a function. It's a block of code, right? It's machine instructions, numbers that are sitting somewhere in the memory of the computer, which can be interpreted as instructions by the processor and can get executed. Okay. So, what happens when you call a function? The CPU jumps to the address of the first instruction of that function and then starts executing instructions one by one, right? If it sees a branch, it will jump somewhere else. If it sees a load, it will get data from memory. If it sees a store, it will write data into memory. Arithmetic instructions will be performed and so on, right? And eventually there will be a return, or which is also a kind of branch, right, which will hopefully bring you back to wherever you left off, right? And of course, we also have a stack frame, that is the data, right, which holds variables that are being used by the function. Okay. And we also have certain conventions that tell us which functions can be called by another function. And as we saw, the main thing that is required over there is, as long as I have seen the declaration of a function at some point, I can call that function. And just the name, the return type and the input arguments are what I need in order to understand the declaration of a function. The interesting thing over there is, once I have seen the declaration of a function, potentially a function could even call itself. Okay. And that is sort of an interesting concept. What does it actually mean for a function to call itself? Right. This is actually related to the mathematical process of induction. You might have come across the notion of proving concepts in math, where we take some kind of a base case, right? Say that, if n is equal to 1, then let us say the sum of the first 1 natural numbers is 1, okay, and then I want to prove that the sum of the first n numbers is n into n plus 1 by 2, right. I take that as my inductive hypothesis. I then say that if it is true for n, I will prove that it is true for n plus 1. I know that it is true for my base case, which is when n is equal to 1, and therefore it is true for all values of n. Okay. A very similar process is what we are thinking of when we talk about this thing called recursion, right. In recursion, what we say is, we once again have some kind of a base case which does not depend on the parameter that we pass to the function, or rather it is something which I do not need to call the function again. I can just look at the parameter and give you the result, right. That is good enough for me, because it means that I am not going to go into an endless loop of calling the function on itself. But as long as I have that, I can then actually say that I can express a function as a recurrence. That is to say, the function is defined in terms of previous or other values or other computed values of itself, right. Some of you may have come across this recursive function in order to implement something like the Fibonacci series, because after all, what is the Fibonacci series? It basically says that the nth number in that series is the sum of the previous two numbers in that series. That is effectively a recursive definition, right. Unless I know what the first two values are, I can't even compute the third one, right. So, if I ask for the nth value, I do not directly have a formula for it. All I say is I can compute it in terms of the n minus 1th and n minus 2th values. Okay. A more common example and a simpler one for us to understand is the factorial function. And what we are going to do now is once again look at how we can visualize the factorial function and use it, and understand how recursion works in that context. So, just like in the previous case, I have this. So, once again I am going to use pythontutor.com in order to visualize what happens when I call a recursive definition of the factorial function. So, first let me look at the function itself and see why it is recursive, right. In what sense is it recursive? I have the function declaration here, int factorial int n. What that means is, it takes one integer parameter or argument as input and generates one integer as output. I have defined int x is equal to 0, this does not really matter. I could also have just taken out this x is equal to 0. I do not really need a definition for x over there, right. I can just leave it blank. And then I have this if condition which says if n is less than or equal to 1, x is going to be equal to 1. Else, that is n is greater than 1, right, x is equal to n into factorial of n minus 1. This is where the recursion happens, right. I am calling the function factorial from inside the function factorial. The important thing to keep in mind is the first time it was called with some value n, the second time it's being called with another value n minus 1, which means that let's say I started off with the value 100, next time it will be 99, then 98, 97 and so on until it becomes less than or equal to 1, that is it becomes equal to 1, okay. And at that point I will promptly return x is equal to 1. Now strictly speaking, this is not a very accurate definition of factorial, because even if I ask for factorial of minus 1 or factorial of minus 100, it will just return the value 1, whereas in reality those are actually error conditions, right. You can't really ask for the factorial of a negative number, but it does not matter, we are going to use this as an illustrative example. Again, this variable x has been brought in simply to help us with visualizing. You could have skipped this and straight away said if n is less than or equal to 1, return 1, else return n into factorial of n minus 1. That would also have worked, but it becomes a bit harder to visualize what's going on, so that's why I have declared an explicit variable out here. And the same way in int, n is equal to 6 is being used inside the main function, just so that I know what value I am asking for the factorial of, and I call the factorial and put the result into another variable called y, and finally printf, okay. So let's visualize this execution, and what you can see out here is that the red arrow is now sitting at the beginning of main, it's all ready to go. What do I have inside main? I have two variables that have been defined, one is n and the other is y, okay. So both of these have been defined out here. Both, when I start execution, all that I can say is I have allocated space for them because I am calling the function main, but they do not have values yet, okay. When will they get values? Let us see, let me start running the code, right. I go into the first line, I have not yet executed line 14, so n is still unknown, but the moment I execute it, n gets the value 6. Now is when things start to get interesting, right. I am going to call the next line 15, which is going to call a function factorial. You can see that it immediately created a new stack frame out here, and now I am inside this function factorial, right. Now what? Inside the function factorial there is another variable called x, which has an unknown value. N is also currently unknown because I have not yet entered the function, but the moment I step into it, I see that n has the value 6, okay. Is n less than or equal to 1? No. Okay, so I am going to go into the next part, and this is where recursion kicks in. Let us take a moment and think about what is happening here. I need to call this function factorial again. I already have a stack frame corresponding to factorial. That stack frame has a value of 6 corresponding to n and an unknown value corresponding to x. What happens when I call this function once again? The answer is it creates a new stack frame. And as you can see over here, this stack frame and this stack frame have nothing in common apart from some name that has been associated with them. They are different areas of memory. The n is different in the two cases, the x is different in the two cases, right. Of course in this case both of them are undefined at this point, but the n is actually different. So n is 6 in the first case, n is 5 in the second case, right, but it has created a new stack frame for that, okay. Let us go further. Once again I find that n is not less than or equal to 1. Once more I create another stack frame, this time with n is equal to 4. Okay. So you can see that I started out with main, I created another stack frame for factorial, then another stack frame for factorial, and now a third one, right. How far can I go? Well, let us see. I go one more step and I find that yet again factorial n is equal to 3. Run it once more and yet again factorial with n is equal to 2, right. Can I keep going or do I need to keep going? Now things are interesting because now I see that factorial, the n is equal to 1. What happens here? let's go back and look at it, is if n is less than or equal to 1. When I step into that code, what I find is it says this x is equal to 1. Let's go look all the way down here. It hasn't updated it yet, but the moment I step into that code, x now gets the value 1. Good. After that, what happens? I have hit the return. So I have the stack frame corresponding to n is equal to 1, x is equal to 1, and when I click next, I am returning from it. You see that stack frame disappeared. It got popped off the stack, so to say, right? I keep creating new stack frames, but as and when a function returns, the stack frame corresponding to it just disappears from the stack. It is of no further interest to us. It is memory that has been freed and returned back to the operating system. Okay. So now I am in the previous stack frame where n was equal to 2, and because I had this x is equal to n into factorial of n minus 1, I find that x gets the value 1 into 2, right. So even though it was a question mark earlier, it now automatically gets the value 2, because it got a value 1 as the return, it multiplied it with this n that was sitting over here and put the value into x. What happens when I continue? I pop back into the previous factorial corresponding to n is equal to 3, but now x takes the value 6, which is this value 3 into whatever was returned from the previous stack, right. Keep going, and n is equal to 4, x is equal to 24. Keep going, n is equal to 5, x is equal to 120, n is equal to 6, x is equal to 720. I pretty much have my answer at this point, right. And when I exit this, what I will find is the factorial stack frames have completely disappeared. I have gone back to main, and at this point y has the value 720. And now of course, I just go ahead, print that value out, it prints the value factorial of 6 and exits the main function. I am done, right. So the main point I wanted to make over here of course was how the stack frames get created and they get discarded once as and when you exit the function, when it completes and exits. Okay. So the reason why recursion can be implemented in C is, number one, this function, the moment I have defined the function out here, I can call it even if it is inside the same function. Okay. And secondly, every time I call a function, it creates a new stack frame that is effectively independent of previous calls to the same function. So they don't sort of clash with each other, they don't collide, and it's perfectly safe to call them one after the other, right. And because of that, a number of especially mathematical recurrence equations, and more importantly certain kinds of data structures such as trees and some types of graph based data structures can be very elegantly and efficiently coded in a language like C, right. There are certain languages that don't support recursive function calls, and in those languages in general trying to implement something of this sort is not a very straightforward thing to do. As you might imagine, assembly language does not have a notion of a function call, right. How would you actually go about implementing recursion in assembly language? It's not a very straightforward thing to do. All of this memory handling, creating a stack frame, keeping track of what values are where and so on, you would have to do manually. Now continuing on the notion of a recursive function call, right, there's one further question that might occur to you, which is what happens if my code either isn't written correctly or does not have this property that I keep reducing towards some condition where finally it's going to do the right thing and exit with. So factorial, for example, I knew that if n is less than or equal to 1, I will get out with the value 1. I don't need to call factorial again, right. But what if I write a code like this, right, where I call demo fun 5 and let's ignore the first two lines, pretty much all that it's doing is once again calling demo fun 5. Okay, that's it just calls itself repeatedly one after the other. Okay. What will happen? Because there doesn't seem to be a base case out here, there doesn't seem to be any condition under which the system can actually continue working, right. So what I have done is I have written this demo fun 5 in such a way that it takes a particular argument, an integer, and it prints what the value of that integer is. Okay. The only thing is this if condition out here is because the printing on screen is a slow process. If I try printing every time I go through the function, what I will find is that actually, it takes forever to basically run this particular program, right? It takes a very, very long time, right? So in order to skip that, what I am doing is I am saying that any time that n is a multiple of 1000, I am going to print out this value, enter %d, and all that means is I am calling demo fun5 for the nth time. Okay, so if it prints 1000 for example, it means I have already called demo fun5 1000 times. Think about it, what does that mean in terms of the stack frames? It means that I started out with one stack frame for main, I have then created 1000 stack frames for demo fun5 being called once, twice, 3, 4, 10, 1000 times. When n is equal to 2000, it means that I have created 2000 stack frames. Okay. Each stack frame by itself may occupy only a small amount of memory, maybe because I don't really have any variables in here. I do have n, right? Remember, I have at least one value that I need to go in there, right? But possibly a stack frame may not be a very large amount of memory that I have, but still it sort of raises the question, can this go on forever, right? Because in principle this looks like I have just created what we would normally call an infinite loop, right? I just call a function again and again and again. The problem with this and why it is not a good infinite loop, unlike for example a while one statement which is a true infinite loop, it will literally continue forever, right, until you sort of interrupt it in some way or switch off the computer. In this case this is not quite the same level of infinite loop. What happens when we run this is, after calling it some large number of times, I run out of memory, right, and the operating system is basically going to kill my program and say enough, now you need to quit. Okay, so let's see when that happens, right? So I'm going to try running this, hopefully it doesn't crash the system, right, but actually it doesn't. What you can see is it very quickly sort of printed out, enter, I've already hit 400,000 out here, right? And what happens is when it gets to something like 520,000, and this number by the way is dependent on the compiler as well as on the operating system. I have tried it with different compilers, different operating systems, and the number actually changes depending on where you are running it. Okay, so it's not like there's anything, this number obviously has something to do with the configuration of the computer you are working with, but it's not predictable without knowing exactly how the operating system works. What is important is, after having been called for a certain number of times, it exited, and what it says is status is -1. Okay. Now this exit status -1 should never normally get printed out here. Basically what it says is the program exited with some kind of an abnormal error condition. To understand that a little better, we can actually go into the shell part of Replit, right, where we have this executable function main, and if I run it, I find that the same thing goes with a slightly different message. It basically says segmentation fault, core dumped. Okay. Now this core dumped part of it is kind of interesting. Basically what it refers to is ancient history in some sense, corresponding to the original operating systems that were being developed for large computers, where there was a concept of the core memory, and a core dump was literally take all the bits that are in the memory and put them somewhere else. Why? So that whoever is sort of trying to debug the program that was written could actually take a look at the state of the computer just before the program crashed. Nowadays in most cases core dumps are sort of turned off by default, so nothing actually gets dumped as a file of data unless you explicitly ask for it. But this message is actually something that, especially when you work with pointers in C, you will come to dread them at some point, right? Don't worry too much about it. All that it says is there was some memory access error. Segmentation fault is again a related term. What it says is the overall memory of the computer is broken into different segments, and because you tried creating so many different stack frames, you effectively tried to access something that was in a segment that was not allocated for you, or outside the range of addresses that you are allowed to access. And as a result, the operating system decided you were up to some not so good business and killed the program. Okay. So this is what is going to happen when you actually try endless recursion, right? It's not likely that you will actually get stuck in a infinite loop, for the simple reason that you actually run out of memory because stack frames have to be created, right? Alright, so that's it basically as a discussion of recursion, how it works and how it gets implemented in the context of C functions.